Hello, welcome to Equity Education, the chemistry version. And today we're going to be looking at spectroscopic techniques, and more specifically we're going to be looking at nuclear magnetic resonance, which is a type of spectroscopic technique. It's just going to be an introduction, so I'm basically just going to introduce some of the key terms and a bit of explanation of how it works. But don't get too bogged down in the explanations because it's really just background information. The things you need to know are the key terms. Okay, so it shouldn't be too long, this one. Okay, so I'd like you to open up your booklet and we will get started. So, some spectroscopic techniques. So we start with a mass spectrometer or mass spectrometry. So a mass spectrometer is used to measure three different uses: the mass of a molecule, the percentage abundance of isotopes, and the chemical structure of a compound using fragmentation ions. So I'm not going to go through any more than that. So this is just an introduction. So infrared spectroscopy. So infrared spectroscopy provides information on the different types of bonds in a molecule, and from this the functional groups present in general. Okay, so there's other videos on these two that if you're unsure about these two techniques, I go back and watch it. Okay, so right, NMR spectroscopy. So an NMR spectrometer provides information on the number and types of environments in a molecule, or the number and types of environments, and the number and types of, are we missing something here? Of proton environments. And from this, the detailed molecular structures can be deduced. So I've just noticed there should be a space here, so let's make a space. Okay, let's try again, and I'll read this through with you again. Right, so we've got two different types of spectroscopy. So an NMR spectrometer provides information on the number and types of carbon in environments in a molecule, or the number and types of proton environments. And from this, the detailed molecular structure can be deduced. So we've got two different types: carbon NMR and proton NMR. Okay, so in chemical analysis, these techniques are used in combination with each other to fully identify a compound. However, the NMR spectrum gives more detailed information than any of the others. Again, just background knowledge. Okay, so NMR spectroscopy. So NMR spectroscopy stands for nuclear magnetic resonance, and it's a powerful analytical tool technique for examining molecular structures in detail. But it also has other applications, such as in body scanning, where it is more commonly known as MRI scanning, so magnetic resonance imaging, which you may have had done at a hospital if you're unfortunate enough to get an injury. Okay, so the two most common types of NMR spectroscopy are proton NMR and carbon-13 NMR spectroscopy, both of which rely on the use of isotopes with an uneven number of nucleons. So nucleons just means protons and neutrons. So really it's the thing in the nucleus. So nucleons in their nucleus. So we've got 1H and carbon-13. Okay, so these nuclei are used because they are able to generate a magnetic field. Other isotopes used include fluorine-19 and phosphorus-31, but carbon and proton NMR are by far the most common. Okay, so I'd just like you to have a go at doing this. So define what an isotope is and work out what the protons, neutrons and electrons are for each of these atoms of the element. Okay, I'm sure you've all been able to do this. So a bit of revision. So isotopes have the same number of protons but different number of neutrons. And I wanted you to fill this table out. So really what we're talking about when we say nucleons is just the number of neutrons and protons added together. Which you will notice that it's the same as the mass number, and all of these have uneven numbers of nucleons, and this is very important. So we have to use one of these when we are doing NMR spectroscopy. Okay, so again, some background knowledge. So the nuclei in these atoms are able to absorb and emit low energy radio waves, which are then picked up by the spectrometer and used in the analysis to produce an NMR spectrum. So when these nuclei absorb energy, they are said to be flipped, or they do flip, or are excited from a low energy state to a high energy state. Okay, and when the nuclei return to the low energy state, this process is known as relaxation. This continual excitation and relaxation is called resonance. Okay, so I'll explain very quickly what I mean. So we've got a low state and we've got a high state, and we can excite the nuclei of an atom to jump to a high state. Okay, if we put the exact amount of energy in through radio waves required for it to get to the high state. Yeah, so it jumps up to the high state. When it falls back down, so when it relaxes, it releases this energy back out. Okay, so this continual moving from high to low is what we call as resonance. And this, in a simplified version, is what we measure when we see a NMR spectrum. Okay, so again, that's just background knowledge. You don't really need to know any more information about that. So we'll carry on. So the electrons in an atom will shield the nucleus from the applied magnetic field in the spectrometer, and the extent of shielding will vary according to the electron. I haven't left enough space here, I don't think, to write up here. Electron density in neighbouring atoms or groups. The environment of a nucleus will have an effect on how much radiation it absorbs in flipping. Okay, so this is quite important. So electrons from neighbouring atoms or groups can shield the nucleus from the magnetic field. So if there's a high degree of shielding, then it requires more energy to get these nucleus to flip. Okay, in the next video we'll go into talk about this in a little more detail. However, this is the thing that you really need to know, and that's the key terms. So we will go through them. So chemical shift. So this is the frequency at which a nucleus absorbs energy. This frequency is measured in parts per million, which you'll see described as ppm, and is compared to a reference peak, which is TMS. Okay, so what is TMS? So TMS, this stands for tetramethylsilane, and it is the chemical used as a standard reference in NMR spectroscopy, and it is given an arbitrary value of 0 ppm. Okay, so what is tetramethylsilane? So if I draw it, it looks like this. Okay, so this is my tetramethylsilane. So TMS has 12 equivalent proton environments. So I've used this word equivalent. Okay, so 3, 6, 9, 12. So it has 12 equivalent proton environments. That doesn't make any sense. It has 1, 2, 3, 4 equivalent proton environments. So each of these CH3s are the same. Yep, they're exactly the same. And this gives rise to a sharp peak that can be easily identified. And TMS is chemically unreactive and volatile, so it can be easily removed from a sample if required. Okay, I'm just going to have a go at drawing something, and I'll be back in a second. Okay, sorry, I should have really drawn this to begin with. So this is something that you may get out of an NMR spectroscopy, a spectrum, and this at 0 would be my TMS peak. So the TMS peak, which has a very sharp, distinctive peak, and it's given the value 0. More often than not, though, the TMS is removed from a spectrum, so you don't get confused. So you may not even see this peak. Okay, and our two axes, so we have absorbance, and we have parts per million down here, parts per million. And you'll see that there's some other peaks here as well. Okay, so I'm not going to talk about them at the minute. You just need to be able to recognize what this looks like. So if our TMS peak was on it, it would be on at 0, and it'd be a very sharp, identifiable peak. Okay, moving on. So a deuteriated solvent. So the deuteriated solvent that we use is D2O. Now we know a solvent dissolves something. So a solvent containing deuterium rather than hydrogen, H, is used so that the solvent's molecular structure does not interfere with the analysis, as D atoms do not produce an NMR signal, e.g. CdCl3. So what we often use is CdCl3, sorry, not D2O, as our solvent. And the reason why we do this is because deuterium has even numbers, so an even number of nucleons, therefore does not produce a signal. Now we said that NMR spectroscopy works because 1 hydrogen and 13 carbon both have uneven numbers of nucleons. So if we use CHCl3 as our solvent, that would produce a signal and it would mess up our spectrum. Therefore, we need to use a solvent that has an even number of nucleons so it doesn't produce a signal on our spectrum. Okay, and moving on. So peak, so even our examples here are our peaks, and that is the line at a particular frequency in an NMR spectrum. Okay, now I'm going to just tell you what these are, but I'm not going to explain anything because that's going to be on the next video. So spin-spin splitting. This is the pattern of splitting of a peak in a high resolution spectrum, resulting from its neighboring atoms. Okay, that's it. I'm not saying anything else. That's it for now. And the integration trace, this indicates the ratio of the number of protons of a particular type in a proton NMR spectrum. Right, I'm probably sure that that doesn't make too much sense, but they're the key terms that you need to know, and we will start to discuss it in more detail in the next video. Okay, thank you. And I hope that was useful as always, and I will see you next time for a bit more spectroscopy. Okay, bye bye.